Hello everybody, welcome to this session. In this session we start designing our board schematic. First we start from SIM800C power section. Okay, so to draw our schematic we need to first create these symbols and their footprints. To do that, I'm going to create my own library that includes all the components that is used in this board. After creating your library, you can use these components in other schematics and other projects. Okay. Before starting to create library, let's look at LM2596 datasheet and also SIM800C datasheet. Learn how to choose these components here and also how to calculate their values. To download LM2596 and SIM800C datasheets, open your web browser and search for LM2596 datasheet. Okay, in Google, search for it, and let's have a look here and download this PDF and save it somewhere. Also search for SIM800C SIMCOM. After that, open this link, the second link in Google search results. Open it in new tab. Okay, and this is that page. As you can see here, there is some details about SIM800C module and its features in here. Open in download section, open SIM800C link in new tab, and you will see the user manuals and guidelines here. Download this PDF, SIM800C hardware design version 1.05. Download this PDF and save it somewhere. After you download it, open SIM800C datasheet. I downloaded before, so I just open it. So this datasheet will help you to choose right components and right values for them. After opening, go to here, contents index, and go to power supply section and click on power supply. Okay, so as you can see here, the datasheet says that the power supply of SIM800C is from 3.4 volts to 4.4 volts, and also you can see here there are some recommendations and guidelines for SIM800C power supply. Go a little down. Okay, as you can see here, in this datasheet it suggested 2 regulators for power supply, one with MIC 29 SIM800C regulator. It's an adjustable linear voltage regulator that can handle current requirements for this module, and you can adjust its output voltage with these two feedback resistors in here. Also, it suggests this DC to DC converter with LM2596 adjustable version regulator. We want to use this schematic for our board with a little change in some components value. Let's look at LM2596 datasheet and see how to calculate these values. You can use both of these regulator in this datasheet, but if you read here, the datasheet says that if there is a high dropout between the input and the desired output, a DC to DC power supply will be preferable because of its better efficiency, especially with the 2 amp peak current in burst mode of the module. So we choose this version because of this high current. Okay, let's open LM2596 datasheet and see how to choose these components and how to calculate their values. This is LM2596 datasheet. It's 3 amp step down voltage regulator. A step down means that the output voltage is lower than the input voltage. It's available in 4 versions. 3 of them is fixed voltage and 1 of them is adjustable output version. We use adjustable output version in our board. It's available in 2 packages. One of them is deep and one of them is SMD. We will use this package in our board. Its switching frequency is 115 kilohertz. That's provided by an internal oscillator, and also it is very high efficiency converter. Let's look at other parts of this datasheet. Go a little down to here, right here. Here we have our converter pin configuration and its functions. As you can see, it has 5 pins. One is V-in, that is connected to our power supply, the output pin, our output voltage, the ground pin, the feedback pin. This pin will be connected to our feedback resistors, and we can adjust the output voltage with this pin and those 2 feedback resistors. Also, we have an on or off pin in here. You can turn on or off your converter with this pin. As you can see here, it says that pulling this pin below a threshold voltage of approximately 1.3 volt turns the regulator on, and pulling this pin above 1.3 volt up to a maximum of 25 volt shut the regulator down. So you can use it to turn on or off your converter. So let's go further. Go to page 27. 14. Here, right here. Okay, so in here the datasheet suggests the circuit that you can use for your applications. If you see the recommended circuit of SIM800C in here, you will see that they use this circuit too. It's very similar with a little change, of course. In here, as the datasheet says, the output voltage here can be calculated by this equation. Also, it says that so from this equation, the R2 will be equal to R1 times V out over VRF minus 1. Also, it says that select R1 to be approximately 1 kilo ohm, use a 1% tolerance resistor for best stability. Okay, we choose R1 in here, 1 kilo ohm, so we need to calculate the R2. These resistors are feedback resistors. We can adjust the output voltage with just these two resistors and this with this equation. Okay, let me draw something here. Our VRF is it's determined in datasheet. It's 1.23 volt, and our V out is 4 volt, and R1 is 1 kilo. So if you calculate with this value, the R2 will be 2.2 kilo. So, as you can see in SIM800C datasheet reference circuit, R1 is 1 kilo and R2 selected 2.2 K value, and also we use this value in our circuit. You can see here. Okay, the C in, which is here, value can be vary from 100 microfarad to even 680 microfarad. It suggests 470 microfarad, 50 volt, aluminum electrolytic capacitor. Be careful about this voltage. Okay, let me close this. Be careful about this voltage and choose a higher voltage from your input power supply. For example, if your power supply is 12 volt, choose C in voltage rating much more than 12 volt, like 30 volt or 50 volt. Okay, your C in will not damage. The C out also can be vary from 100 microfarad to even 1000 microfarad. Okay, it suggests 220 microfarad. Don't choose a small value, for example under 100 microfarad. Also, don't choose very big value, because on startup and after you turn on the board, this capacitor will be discharged and short circuit. So if you choose very big value, it will draw a huge current to be charged and your regulator will damage. Okay, so don't choose very high values and don't choose even under 100 microfarad. 220 is good. The reference circuit selected 230 microfarad. We choose 680 microfarad. Okay, so to choose D1, this diode in here, go to page number 18. It's a little up. It's here, right here. They call it cache diode. Read these guidelines. It says that buck regulators, buck means a step down. It means that the output voltage is lower than the input voltage. Buck regulators require a diode to provide a return path for the inductor current. When the switch turns off, this must be a fast diode. Because of their very fast switching speed and low forward voltage drop, Schottky diodes provide the best performance, especially in low output voltage applications like 5 volt and lower. And it also says that rectifiers such as the D1N 5400 series are much too slow and you should not be used. So as you can see here, it says that you can use slow diodes like 1N 407 or 401. They are used for rectifiers. Don't use them in this application. Also, you can see that the reference circuit of SIM800C used MBR 360. It's a Schottky diode, and its current rating is 3 amp. You can use 1N 5822 diode also in here. As you can see, we used it in here. It's a Schottky diode with 3 amp current rating. It's very similar to this one, MBR 360, and you can find it easily on market. It's very cheap. Go back to page number 27. Here. There are two components left, the L1 inductor and CFF. FF stands for feed forward. Actually, we don't need this CFF in our application. Go to page 17. 17 right here. It says that a feed forward capacitor shown across R2 in table 6 is used when the output voltage is greater than 10 volt. Our output voltage is 4 volt, so it's not greater than 10 volt. Or when C out has a very low ESR. I'll tell you what is ESR. So for this reasons we don't need this capacitor, okay, so we don't use it. Go to page 27 again. It's here, okay. The last component is our inductor. Go to 28 right here, inductor selection in here. To choose the value of our inductor, first we need to calculate, as you can see here, the datasheet says that calculate the inductor volt time microsecond constant E times T with this equation. So we need first calculate this equation, okay? In this equation, V in is our power supply voltage, that is 12 volt. V out is 4 volt. V sat, as you can see here, is 1.16 volt, and VD is 9 volt, and you can calculate this equation with these given values. So if you calculate it with these values, it will be equal to 18.22 volt microsecond. After that, go to page number 20. It's just here. So there is a diagram in here for adjustable version. In here we should use this diagram. This diagram help you to choose your inductor value. In this diagram, as you can see, horizontal axis is maximum load current, and the vertical axis is E times T that we calculated before. Its value is 18.22 volt microsecond. Our current, maximum load current, as I said before, our GSM module draw a 2 amp current when it's going to connect to network, but in this case this current is not continuous. It just happened when it's going to connect to network. Our continuous current is the current that will drawn by our GSM module when it's in normal situation, and our indicator LEDs. It's something about 1 amp. So our current is 1 amp, and our E times T value is about 18. So if we see here, our inductor will be about 68 microhenry. But because of that 2 amp current peak, this current is just happened in a few microseconds, okay? It's not continuous. But because of that 2 amp current peak, we need to choose higher value like 100 microfarad for our inductor, okay? As you can see here, the reference circuit of SIM800C choose 100 microhenry inductor 2. We choose all the components that we need for this converter, as you can see here, page 27 here. We choose all the components that is recommended by this reference circuit in LM2596 datasheet. Let's look at SIM800C reference circuit again. There are 3 more components that doesn't exist in LM2596 recommended circuit. First one is this FP101, and the second and the third one is this 100 nanofarad and this 1 microfarad capacitor. FP stands for ferrite bead. It's a kind of inductor. It's optional here and you don't have to use it. It can eliminate high frequency harmonics that exist in current. It's not relevant to our discussion in this course, and we don't use it. But these two capacitors are very important. We call them bypass capacitors. You usually see them in other boards' power sections. They usually come along with a high value bulk capacitors. Bulk capacitors, when I say bulk capacitor, I mean these large value capacitors that in input and output of our converters or regulators, like this 100 microfarad or this 330 microfarad capacitor. The reason of using them is capacitor impedance with frequency. Let me show you this picture. Where is it? This picture. This is the equivalent circuit of a capacitor. All capacitors have ESL, ESR, and R leak. ESL means equivalent series inductance, and ESR means equivalent series resistor. This resistor in here are leak stands for leakage. This resistor is because of capacitor leakage. It's a model for capacitor leakage, and it has very high value. You can delete it from here. It's not very important in our case. As you know, the impedance of a capacitor is 1 over j omega c. Let me draw something in here. Smaller. So ZC, that is impedance of a capacitor is 1 over j omega c, right? Omega is frequency. As the frequency increase, the impedance decrease, right? So if the frequency is infinite, the impedance will be equal to 0. But in real world, this does not happen. From a frequency onwards, impedance, the inductive property of this capacitor will dominate the capacitive property. So the capacitor will act as an inductor. The impedance of an inductor is ZL equal to 1 over, ZL is equal to J omega L. The impedance of an inductor is J omega. Higher frequency, higher impedance, right? So from a frequency, as the frequency increases, the impedance will increase too. We call this frequency resonance frequency. Let's look at another picture in here. We have three different value capacitors with different packages. Okay, the horizontal axis is frequency and the y-axis is impedance. As you see here, the impedance will decrease until the frequency, right? This frequency. After that, it increases. As you can see here, the blue curve in here. If you use two capacitors with different values, the impedance diagram will be something like this yellow one. Okay, if you use these three capacitors in parallel, the equivalent diagram will be something like this yellow one. As you notice, the impedance of lower value capacitor like this will decrease in higher frequency, right? This capacitor has lower value than this, so its impedance will increase in higher frequency versus this one. That's the reason that we use two capacitors in parallel for bypassing. A large one for bypassing lower frequency noises, harmonics, and a small one with different package for bypassing high frequency. If you see our schematic in here, you will see that we used two different value capacitors with different packages. One of them for bypassing low frequency harmonics, and another one for bypassing high frequency noise harmonics. I hope you understand the reason that why we use always a lower value capacitor along with a higher value capacitor in our power sections. Our board power section is approximately completed. We also use this indicator LED in here that indicates that our board is on or off. So our power section circuit is completed. Now we can start creating our library and draw our schematic.